Welcome to this explainer produced by Forge College. If you've been following along in our track from EVM to SVM, transitioning from Ethereum to Solana, you know we've been tackling the underlying mechanics of client architecture. In our previous lesson, introducing RPC patterns in SVM client architecture, we mapped out the theoretical differences between request response models and subscription models. Well, today we're translating that theory into actual, hands-on practice. We're going to map those RPC pattern decisions directly to your everyday developer workflows and turn your chaotic network requests into a resilient, production-ready survival guide for your EVM to SVM transition. Let's dive in.
Aw man, it's the universal pain every single Web3 developer feels, right? You write some perfectly good code, you fire up your application, and almost immediately you start hitting rate limits. You experience dropped WebSocket connections, and you watch these annoying transient network glitches just ruin everything. It's literally enough to make you want to throw your laptop straight out the window. But instead of relying on pure luck or angrily spamming that refresh button, we're going to build some concrete architectural strategies to handle these failures gracefully. All right, here's our agenda for today. We're covering 1. The RPC Survival Guide. 2. Mastering Exponential Backoff. 3. The Power of Batching. 4. Taming WebSocket subscriptions. 5. Testing the ultimate snippet. And 6. Observability and next steps. Okay, let's jump right into Section 1, the RPC Survival Guide, where we'll diagnose the root of the problem. So let's start by looking at the core issue here. Because look, if you don't correctly identify the type of error you're facing, your retry logic is actually going to make the problem a whole lot worse. This perfectly illustrates the great divide in network debugging: transient versus permanent errors. Transient errors, like your HTTP 5xx responses, timeouts, or random connection drops, essentially just mean, hey, try again later. Permanent errors, on the other hand, like HTTP 4xx responses or a malformed JSON payload, mean your request is fundamentally broken. Knowing the difference between these two is absolutely critical for safely maintaining idempotency and making sure we don't accidentally execute the exact same state-changing operation twice. To handle these, we have 3 main connection strategies. Immediate retry is great for low-latency reads where failures are incredibly rare. Then you have exponential backoff, which is your heavy lifter for dealing with rate limits and those transient glitches we just talked about. And finally, queued batching is your efficiency engine. It's going to reduce your overall request overhead whenever the RPC node actually supports it. Moving right along to Section 2, Mastering Exponential Backoff. Let's talk about handling those pesky transient errors. Let's dive into our first survival tool. When you hit a transient error, you need a strategy that handles the failure without aggressively hammering the node. Think of it as the polite way to knock on a grumpy neighbor's door. If you spam the doorbell, they're just going to ignore you, or, in node terms, slap you with a strict rate limit. But if you wait a bit longer between each knock, increasing the delay interval each time, they are much more likely to actually answer. This brilliantly prevents the dreaded thundering herd effect, where thousands of clients retry at the exact same millisecond and accidentally take down the entire RPC node. Nobody wants to be that guy. But here is the crucial takeaway. Stop retrying permanent errors immediately. I mean it. If an error is permanent, like a malformed request payload, do not keep retrying it. Your backoff loop needs to actively inspect that error message. If it's a 400 bad request, you break the loop and throw the error. Persistently retrying permanent errors is just going to break idempotency or cause absolute application-level chaos. All right, Section 3, the power of batching. Let's look at reducing request overhead. If backoff is about how you retry, batching is all about how you pack. It's exactly like bringing a comprehensive grocery list with you instead of driving back and forth to the store for every single individual item. Our Node.js batcher class works through a highly efficient pipeline to do exactly this. Step 1. You enqueue a request, which generates a unique ID and returns a pending promise. Step 2. The queue just waits until it either hits a maximum batch size, say 10 items, or a time limit, like 50 milliseconds. Step 3. It flushes that queue as a single JSON-RPC batch payload. And finally, Step 4. When the bulk response comes back, it smoothly maps the response IDs back to resolve your original promises. The result of this workflow? It's honestly incredible. By accumulating these requests, we drastically reduce request overhead, effortlessly turning a dozen separate slow network pings into literally one highly efficient JSON-RPC batch call. Your application code stays completely pristine, just awaiting promises as usual, while the batcher handles all that heavy network optimization right under the hood.
Next up is Section 4, Teaming WebSocket Subscriptions, managing those stateful streams. Now, unlike your standard HTTP requests, WebSockets actually stay open, which introduces a whole new set of developer responsibilities. Because they're stateful, your subscription manager has to handle specific lifecycle rules perfectly. Otherwise, your app is going to leak resources when connections inevitably drop. You absolutely must auto-reconnect on close events, and critically, you need to replay subscriptions on open. If the network blups, the node totally forgets what you were listening to, so your client must automatically resend those subscription payloads once the ready state is open again. That is how you ensure your application state remains perfectly consistent. Which brings us to Section 5, testing the ultimate snippet, time to validate our core behaviors. So let's bring our three tools together. We take our exponential backoff, our batcher, and our subscription manager, we combine them into a unified, reusable Node.js code snippet, and we run a smoke test. Here's a quick diagnostic of what your console log should actually look like. In a good run, you're going to see a single batched HTTP post go out, the response IDs will seamlessly match your queued promises, and your WebSocket logs will gracefully stay connected. But in a bad run, you'll see repeated permanent errors because your classification logic is flawed, or promises hanging forever because your node doesn't actually support batching, or maybe a WebSocket just endlessly reconnecting due to a blocked port.
Finally, Section 6, Observability and Next Steps. Let's bridge this over to deployment. So with a tested working snippet in hand, how do we bridge this localized development workflow into a full-scale, robust deployment strategy? Well, one of the most important takeaways you can learn today is to live by this rule. Use environment variables for your HTTP and website URLs. Never, ever hardcode your endpoints. By keeping your network configuration external, you ensure your client is effortlessly portable. You can switch from local testnets to enterprise mainnet nodes instantly without having to change a single line of your core logic. And hey, you cannot deploy what you cannot measure, right? So add these simple observability signals to your code. Log your backoff durations, monitor the timing of your batch flushes, track exactly how often your websites drop, and add metrics counters. By doing this, you'll be fully prepared. These logs are the exact signals you're going to need for our next lesson, where we'll tackle deployment strategies, connection pools, and sidecar proxies. We've built some serious resilience into your code today, but consider this. In a decentralized world, network instability isn't a bug, it's literally a fundamental feature of the architecture. If your application expects Web 2 perfection, it is going to fail in Web 3. So ask yourself, are you building clients that simply survive the chaos, or clients that are engineered to thrive in it? That wraps up our RPC Survival Guide, an explainer proudly brought to you by Forge College. Make sure to visit forge.college to dive deeper, access our interactive coding exercises, and continue your transition from EVM to SVM. Keep building resilient clients, and we'll see you in the next lesson.